Gate exam questions with solutions in power system syllabus part 1. So question number 1, the geometric mean radius of a conductor having 4 equal strands of radius r as shown in figure below. So here you are having 4 strands and the radius is r. The question asked to find the geometric mean radius of a conductor, and here it is a stranded conductor. So the options are 4 into radius r, or 1.414 r, or 2 r, or 1.723 r. Solution. So given that each of 4 strands, so we represent that strands as S1, S2, S3 and S4, and all the 4 strands having the same radius r. And the geometric mean radius GMR for a single circuit, or we call this as self GMD, self geometric mean distance, represented as r dash, that will be equal to 0.7788 into r, where r is the radius of a conductor and this r dash is the fictitious radius of a conductor. Consider the given diagram. So from the given diagram, so we can find the GMR for each conductor. For a single circuit, considering the first conductor S1, the self GMD, self geometric mean distance is r dash, that is 0.7788 into r, and the mutual distance, geometric mean distance between conductor S1 and S2, between strand S1 and S2 is 2r. So since the radius of both the conductors are same, you will get 2r. So 1r is from the center point to this outer surface is r, and the second one is this radius. So it becomes 2r. Similarly, the distance between the two strands S1 and S3, it is 2 into r. And the geometric mean distance between S1 and S4, that can be determined using a Pythagoras theorem. Consider the right angle triangle and apply Pythagoras theorem. Root of this distance 2r square and the root of this distance. This distance is also 2r. So root of 2r square plus 2r square, that gives you root of 8r square, and that will be equal to 2 root 2r. So now the geometric mean radius for multiple circuits. So here in this case we are having 4 strands of conductors. So we can apply the geometric mean radius for multiple circuit and find the GMR for the complete conductor. So GMR equal to 4th root of S11, which is self GMD, and S12 into S13 into S14. So substituting all the values we found in the previous step. So 0.7788 into r, 2r and 2r into 2 into root 2 into r. Taking r as common, you will be getting r power 4, and multiplying this term, you will be getting 8.811 into r power 4. 4th root of 8.811 is 1.723 r. So GMR is 1.723 r. So out of the 4 options, the correct option is option D, that is 1.723 r. So now we move on to the second question. Question number 2, the valid positive, negative and zero sequence impedances in per unit respectively for a 220 kV fully transposed 3-phase transmission line from the given choices are. So they asked to find the valid positive, negative and zero sequence impedance for the fully transposed 220 kV transmission line. So in the option, the values are the positive and negative and zero sequence impedances. So first one is positive, negative and zero sequence. Similarly for the other options. So which option is a correct value, that we need to find. Solution. For a fully transposed 3-phase line, the condition is x1 equal to x2, and that will be equal to xs minus xm. It's the first equation, and x0 equal to xs plus 2xm, where this xs is self reactance, xm is mutual reactance, and x1 is positive sequence reactance, x2 is negative sequence reactance, and x0 is zero sequence reactance. So this is a condition, the first and second equation. And now from this 2 equation we get this x0 term. So x0 equal to xs plus 2 into xm. This is somewhat greater than this first equation, that is x1 equal to x2 equal to xs minus xm. So the value will be less when compared to x0. So the condition is x0 is greater than x1 equal to x2. So that is your third equation. Now the option which satisfies the equation 3 is the correct answer. So the equation 3 says x0 is greater than x1, that is equal to x2. In our option we are having x0, x1 and x2. The options are A option is 1.1, 0.15 and 0.08. So this is x1, x2 and x0. So out of these 4 options, we need to check which option satisfies the third equation. x0 is greater than x1 equal to x2. So first condition is x1 equal to x2. So here A option x1 is not equal to x2, so we reject that one. And D option also x1 is not equal to x2, you can eliminate that one. And C option 0.2 and 0.2, and all these 3 values are same. So 0.2, 0.2 and 0.2, but x0 must be greater than x1 equal to x2. So we can select the B option. So here you can see x1 is equal to x2 and this x0 is greater than x1 equal to x2. So the option B is the correct answer. So from option B, x1 equal to x2 equal to 0.15 and x0 equal to 0.35, that is greater than x1 equal to x2. So option B satisfies the equation 3 and hence it is the correct answer. The correct option is B. Now we move on to the third question. Question number 3. The fuel cost function in rupees per hour for two 600 megawatt thermal power plants are given by, for plant 1 C1 equal to 350 plus 6 P1 plus 0.004 P1 square, and plant 2 C2 equal to 450 plus A into P2 plus 0.003 P2 square. So where this P1, P2 are power generated by plant 1 and plant 2 respectively in megawatt, and A is a constant. The incremental cost of power lambda is 8 rupees per megawatt hour. The two thermal power plants together meet the total power demand of 550 megawatt. The optimal generation of plant 1 and plant 2 in megawatt respectively are P1 and P2 that we need to find. These are the options. So now the given cost function we are considering C1 and C2. Solution: find the incremental cost. The incremental cost simply by differentiating the cost function C1 and C2. If you differentiate this, the first equation 2 into 0.004, that gives you 0.008 plus 6. The second term is, if you differentiate, it becomes 6, and third term is a constant one. And similarly for second equation C2, it is 2 into 0.003, that is 0.006 plus A, and 450 is a constant one, just leave it. Okay, so this is your incremental cost, simply differentiating C1 and C2. And now for optimum generation, this increment cost will be equal, and that will be equal to lambda. So IC1 that will be equal to IC2 and that will be equal to lambda, and lambda is given in the problem as 8. Now equate the first equation, IC1 equal to 8. So we know IC1 is equal to 0.008 P1 plus 6, that will be equal to 8. Simplifying, so P1 equal to 6 goes that side, it becomes 8 minus 6 divided by this 0.08, that gives you 250 megawatt. So P1 equal to 250 megawatt. And we know the total load is 550 megawatt, that is P1 plus P2 equal to 550 megawatt. So P1 we know, so we can subtract from the total load. So 550 minus this 250, that gives you 300 megawatt. So P1 equal to 250 and P2 equal to 300. The correct option is B, 250, 300. Question number 4. The generator has a cost function F1 and F2, then the incremental cost characteristics are dF1 by dP1 equal to 40 plus 0.2 P1. So dF2 by dP2 equal to 32 plus 0.4 P2. The need to deliver a combined load of 260 megawatt ignoring the network losses for economic operation of the generation of P1 and P2 are. So here also they asked P1 and P2 for this particular condition. So the options are P1 equal to P2 equal to 130, and P1 is 160, P2 is 100, P1 is 140, P2 is 120, P1 is 100 and P2 is 160. Solution. So given incremental cost function is this one, the combined load is 260 megawatt. Now the incremental cost of first generator, that will be equal to incremental cost of second generator. So this is the optimum condition. IC1 equal to IC2. Just equate this two equation. 40 plus 0.2 P1 equal to 32 plus 0.4 P2. So now this 0.2 P1 and bring this 0.4 P2 to that side, it become minus 0.4 P2, and 32 and 40 bring this side, it become minus 40. So the answer will be minus 8. So 0.2 P1 minus 0.4 P2 equal to minus 8. This is your second equation. The first equation is the combined load P1 plus P2 equal to 260 megawatt. Simply solve this two equation in the calculator using a equation mode, or simply solve this two equation and find the answer, that is P1 equal to 160 megawatt and P2 equal to 100 megawatt. So the correct option is B, P1 equal to 160 and P2 equal to 100. Question number 5. A 20 MVA 11.2 kV 4 pole 50 Hz alternator has an inertia constant of 15 megajoule per MVA, and if the input and output powers of the alternators are 15 megawatt and 10 megawatt respectively, the angular acceleration in mechanical degree is, and we need to round off this to nearest integer. So from the given data we need to find the angular acceleration in mechanical degree per second square. Solution. So the given data is Pm equal to the mechanical power equal to 15 megawatt, electrical power P equal to 10 megawatt, and the mission rating of alternator is S equal to 20 MVA, and the inertia constant H equal to 15 megajoule per MVA, frequency 50 Hz and number of poles 4. So from the given data, and we are considering the swing equation of an alternator, so the acceleration is given as d square del divided by dt square, that will be equal to alpha, and that will be equal to Pa by m, where Pa equal to Pm minus Pe, the mechanical power minus electrical power. So mechanical power is 15, electrical power is 10, so you will be getting 5 megawatt, and m is equal to Hs divided by pi into F, where H is inertia constant given as 15 and S is the mission rating 20 divided by pi is 180 and frequency is 50. If you substitute, you will be getting 0.0333. Alpha equal to Pa by m. So 5 divided by 0.0333, that will be equal to 150 electrical degree per second square. So this alpha is the electrical degree per second square, but in question it is asked to find the mechanical degree. So in mechanical degree, simply by multiplying the answer with 2 by P. So 150 into 2 by number of poles P is 4, you will be getting 75 mechanical degree per second square. So the correct answer is 75 mechanical degree per second square.